Today, we're going to talk about function transformations, okay? And the rules that we learn today are going to hold true for every single function no matter what. Okay, what that means is we are going to learn ways to move functions. We're going to move them left, right, we're going to flip them, we're going to stretch them, we're going to do whatever we need to do to them. Okay? So, the function that we're starting off with is f of x equals 2x squared minus 3. F of x equals 2x squared minus 3. Okay, so in your calculator, if you want, if you do not want and you just want to follow along, that's fine also. Okay? In your calculator, in y1, you're going to put 2x squared minus 3. Yes, just sorry, my pen was not acting correctly. Okay. I'm not sure. It's a good question. Okay. All right. Hold on. In y1, I would like for you to please type in your original function that is written for you at the top of your paper. 2x squared minus 3. Graph that and see what it looks like. The parabola, is the vertex above or below the x-axis? Below. What do you think the line of symmetry is? Not the x-axis. The y-axis. The y-axis is our axis of symmetry. Okay? This is the function that we are going to be manipulating. We're going to be moving it left, right, up, down. We're going to be stretching it, compressing it, flipping it. We're going to be manipulating this function. This is our starting point. Okay? This is our starting point. So, the first thing I want you to do is look at number 1. It says try f of x equals 2x squared. Oh, no, I'm sorry. Leave the original function in there. I shouldn't have started typing over there. Sorry. Leave the original function in where it was. 2x squared minus 3. Okay? Now, we are asked to take this whole function and add 2. So that's what we're going to do. In y2, we're going to type in our original function, 2x squared minus 3. We're going to add 2. All right? You will it will be helpful if you arrow over on the other side of y2, and you press enter. Press enter, and it will turn that line to bold. Okay, so let's graph it. Here's our original function, and here's our new function. What has happened? It moved up. How much do you think it moved up? 2. Where could you check that? In the table. Okay? So, we took our whole function, our whole f of x, and we added 2. So when we take f of x and we add a to it, what's going to happen? Move up a. What about if we subtract a? Move down. Yep. So these arrows, these like little bullets right here, these are setting up our general rules. So a is any number. Any number that you add or subtract, these are our general rules. Okay? All right. So that's what happens when we add or subtract a number from the whole function. Okay? Let's see what happens. Before we see what happens with number 2, I want to tell you a little something about math. Okay? From my experience, and I think if you ask other people that have had a lot of math experience, they'll agree with you. Okay? There are times in math when every once in a while you're just going to have to throw up your hand and say, okay, fine, you win. You win math. I have no idea what you're doing. I don't understand it, but I'll accept it, and I'll memorize it, and I'll do it. Okay? There's going to be some times today where you might feel that way. You might feel like, why in the world is this happening? Okay? But it will click in good time. You're just for now going to have to say, okay, for now I'll just learn your rule, and I'll do it. Okay? Okay. So on this one, instead of adding or subtracting a number from the whole function, we're only adding or subtracting a number from x. In this case, we are subtracting 2 from just x. Okay? So let's type this in to our y equals. Keep your original function there. You can just type right over the function you had. Okay, and let's watch what happens. Here's my original function. There's my new function. What happened? It moved which way? It moved right 2. Now, when you see x minus 2, which direction do we think it's going to go? Left. Okay? Whenever you're messing with the inside, when you're messing with x's, weird stuff happens. Okay? In this case, it's always opposite what you think is going to happen. So we subtracted 2 from x, and what happened was the graph moved right 2. It moved opposite what we thought would happen. Okay? So anytime I do f of x minus a, I subtract a number from x on the inside, which direction is my graph going to move? Right. Opposite what you think would happen. Okay? It's going to move right a units. Okay? How about f of x plus a? It's going to move left a units. Okay? Questions on that? It's opposite. It's weird, but that's how it works. Okay? All right. Let's look at number 3. Okay? Let's look at number 3. In our first one, we're going to take our whole function and we're going to multiply it by 2. We're taking our whole function and we're multiplying it by 2. It's 2 times 2x squared minus 3. All right. Let's graph it. Here's our original. Here's our new function. Okay? In order to really see what's happening here, let's look at our table. What do you notice about your 2 y values? They doubled. They were multiplied by 2. Okay? That makes sense if we think about the fact that we took our function and what do we do to it? Multiplied by 2. Okay? Okay? So what happened was the y values were multiplied by 2. Okay? What we call that you could put on your rule, anytime you multiply your whole function by an a value or a number bigger than 1, what we call that is a vertical because we're messing with the y values, a vertical stretch. Stretch because it's getting elongated. Okay? Yes?
Does that say the negative y values?
Nope, sorry, just y values. Multiply y values by 2. Okay? All right, let's think about what's going to happen if we type in 1/2 instead. All right, so let's watch it. Remember, we're multiplying the whole function by a value. So when we do stuff with the whole function, we're messing with the y's. We're not messing with the x's. Let's graph this. Here's our original function, and here's our new function. Okay? It hasn't gotten, I don't want you to think of this as getting wider. Okay? What I want you to think of is look at your y values. Look in your table. What's happened to each of your y values? It's divided by 2. So don't think of it as getting wider. Think of it as it's gotten compressed from the top and the bottom. Every y value has gotten divided by 2. Okay? Or we could say multiplied by 1/2. Either one. Okay? So what happened was we divided the y values by 2. So anytime we plug in a number here between 0 and 1, any fraction, we call that a vertical compression. Vertical because my x values have not changed. It's only my y values. Questions? Okay. Let's look at number 4. Number 4 says, what does it look like we're going to be doing here in number 4? Good. This time we're just multiplying x. Last time we multiplied the whole function. This time we're just multiplying by x. Okay? Okay. So, let's type this in. Remember, the last time we were in with the x's, things got a little weird. They're going to get a little weird here too. Yay, indeed. 2 times 0.5x. Not on the very outside, you don't. Okay. You ready to watch? Here we go. Here's our original. And here's our new function. All right. Use your vertex to kind of get a grip on what's happening. On your vertex, did the y value change? No. Okay? The y value didn't change. The x value stayed the same, okay, for this particular case because the vertex is at 0, -3. But look at like this y value right here. That y value stayed the same, but our x's got what? Bigger or wider. This is a horizontal stretch. We're messing with the x values, so it stretches our graph. Now, when we see 1/2 times x, do we think it's going to be a stretch or a compression? Think it's going to be a compression, right? Because it's a fraction. But remember, when things are in the inside with the x, they get really weird and they go opposite. Oops, wrong one. Sorry. That's not the one we're doing. We're doing this one. Okay? So, this one caused a horizontal stretch. Okay? So is that going to go on my top rule or my bottom rule? The bottom, because my A value is 1/2 between 0 and 1. So this is a horizontal stretch, opposite from what we would think. What do you think is going to happen with a number bigger than 1? It's going to be a horizontal compression. Okay? Horizontal compression. Okay, now with the negatives, let's see what happens. What do you remember from just your past experiences negatives normally do with a function? They might flip it upside down, right? That's exactly what's going to happen. Let's type that in. Negative 2x squared minus 3. Okay? Here's our original function. There's our new function. What's happened? Flipped. Reflection across the x-axis. Now let's think about that, if that makes sense. What has changed? Our x values or our y values? Okay? These are our y values changed, right? They stayed at 0, but it went up to positive 3. This was up here, it went down here, okay? Look at what that equation looked like. It was a negative in front of the whole function. Whenever we do stuff to the whole function, we're changing the y's. Okay? Whenever we multiply or add or anything like that to the whole function, we're changing the y's. So, this was a reflection across which axis? Yep. All right? What do you think is going to happen if we just put a negative with x? Okay, maybe nothing on this particular graph, right? But what happens in general? It's going to flip. What's going to change now? The x values or the y values? The x values. So what axis are we going to be reflecting across? The y-axis. Okay? Now, if you were to type this in for our particular example that we used, will you see anything different? Yeah, exactly. Our graph that we're using for our example is symmetrical across the y-axis. So a reflection isn't really going to show us anything. But can you imagine how with other graphs, taking f of negative x, you will see a difference? You'll see it flip. Yeah? Okay. Let's keep going. Now's when things start getting a little interesting. Okay? All right. We're going to talk about taking the absolute value of the whole function, and we're going to talk about taking the absolute value of just x. Okay? Two different things are going to happen. Remember what I said. It might not always make a ton of sense, but it will click at some point. Okay? All right. So, let me show you, for those of you still typing these in your calculator, let me show you how we're going to type this in. For the number 6, we want the absolute value of the whole function. Okay? So, we're in y equals. You're going to press math. You're going to arrow over to number. And you're going to choose ABS. That stands for absolute value. Okay? If you have one of the newer calculators, you might have 2 lines that came up, the absolute value symbol. Okay? If so, you want to type in between those 2 lines. If you have one of the older operating systems like mine, you'll just see the ABS come up, okay? And you'll just want to type in your function in there. All right.
Miss Grossman, I just really confused myself on my calculator. Can I watch you?
Okay? All right, let's watch it. Ready? Watch up here. Here's our original. Here's our new. All right, let me show you one more time. I'll show you one more time. Shh. Contain your excitement. Let me show you one more time. Ready? Here's your original. Here's your new. Okay, let's talk about why this happened. Daniel?
Negative values. The negative y values got reflected up.
Yeah. Did anything happen to our positive y's? Nope, our positive y's stayed the same. Our negative y's got reflected across the x-axis in order to make them positive. Now this makes sense because the absolute value of any number is always going to be what? Positive, which means my final graph must all be positive. Okay? So we're going to write that out for us. So what happened was all y, basically we can put that all y's became positive. Okay? So the rule is for the absolute value of the whole function, the absolute value of all of f of x, your rule is keep your positive y's and reflect negative y's across the x-axis. Keep your positive y's and reflect your negative y's across the x-axis. Okay? Questions on that? Okay. In order to better see what happens when we take the absolute value of x, just x, on the inside, we're going to use a new function for this because ours doesn't show it very well. So we're going to use this function as our starting point, and then this is going to demonstrate what happens. So let's type in that new starting function, x minus 3 squared minus 5. Okay? And this time, I'm only putting the absolute value around x. So I need to open a parentheses. Math, number, absolute value. I'm going to keep my x in, that's what I'm taking the absolute value of. I'm only taking the absolute value of x. Okay, then I'm going to subtract 3, square all of that, and subtract 5. All I've done from changing this was put absolute value around that x. Okay? All right, are you ready? Watch. Here's your original. There's your new. All right, I'm going to do it one more time. All right, here you go. One more time. Here's your original. Here's your new. Okay, let's talk about what happened here. What part of our graph didn't change at all? The right side, which is, tell me in terms of x's and y's. Positive x's, okay? The right side of this graph did not change. We kept all of our positive x's, Okay? What happens, though, is we get rid of any negative x's. We literally cut them off and throw them away. Okay? We cut them off and throw them away. In order to fill their space, what we're going to do is we're going to take the positive x's and reflect them to fill their space. So the green and the pink is our final graph. Okay, let me tell you that one more time. Okay? The part that stays the same are your positive x's. That nothing changes over there. We keep it. Okay? We take out all the negative x's. We don't want them, can't use them, they're dead to us. Okay? In order to fill their space, we're going to reflect the positive x's over the y-axis. Okay? Yes? I'll try and explain it to you. I'm happy to do that, but yeah, this is one of those where it took me, I'll be honest, it took me a long time for this to click. Okay? Here's why. All right? What happens if you plug in a -1 to that equation? What does it act like? Immediately, because what's the very first thing we're going to do? We're going to take the absolute value first, right? So even though we're going to plug in -1, immediately it's going to act like +1. That's why we're taking the value from +1 and putting it in the place of -1. Because -1 is going to act like a +1. Okay? All your x values, all your negative x values are going to act like positive x values. Okay? Carolyn? This is the rule for any function no matter what. No matter if it's just a zigzag random pattern like you're going to have on your homework. Keep the positive x's, that's part of your new graph, and reflect it to fill the second part. Okay? Okay, let's write this out so you know what we're doing. So, absolute value of just x has two parts. The first part is to throw out all your negative x's. Throw out all negative x's. Okay? You're going to keep your positive x's, and you're going to reflect positive x's across the y-axis. You might want to also write keep your positive x's so that you remember that that's part of your graph. But when you are telling me the transformations, you don't have to write that down. Okay?
So is this how the actual, so this is how we're gonna like write it down? Like, you know, the two things, or like, are we gonna ignore one first?
So we're going to practice these, and you're going to see how you would be asked this question. Okay? You're either going to be asked to graph, or you're going to be asked to explain the transformations. Let's practice explaining the transformations. Look at number 8. Now, our original function is f of x, just a random f of x. And we are asked to name all the transformations of the absolute value of f of x minus 2. Okay? When you're listing transformations and when you're graphing, you always want to start closest in to the x and work your way out. So, let's see what we're going to do first. The first move we're going to make is we're going to do these absolute values because that's closest to our x. Okay? So our first step, when I'm taking the absolute value of the whole function, what happens to my graph? reflects negative y's across the x-axis. What's the next transformation that's going to occur here? Good. We need to deal with this minus 2. It's on the outside of my function, so it's going to move us down 2. All right? Look at number 9. Start closest to our x and work outwards. What should we start with first? Yeah, this plus 2. What does that plus 2 tell us to do when it's inside the parentheses? Left 2. Good. This is the one that's weird because it's inside your parentheses. What's the next transformation we're going to do? This 2/3. What's that going to do? Okay, it's going to change the steepness. Look back at your notes and see what we called it. Okay, what you're going to do is multiply the y values by 2/3, but what do we call it? Good, a vertical compression. Great. You don't have to. That's for you to know, because sometimes you're going to be asked to graph. So you want to know what you're doing to the y values when you stretch or compress it. Okay, let's try number 10. Number 10 has 4 transformations. Okay, sorry. Just like f of x was our original function here, in number 9, h of x was our original function. So that's all that h and x stand for. Okay? Good question. I should have pointed that out. In number 10, what's our original function? G of x. Good. Okay. What do you think is the first transformation we're going to need to perform? Good. All right. Look back at your notes and let's see what we're going to do. First, we're going to throw out all negative x's. And then what are we going to do? Nope. Look where our absolute value is. This absolute value is around just the x. So we're going to follow rule number 7. And we're going to reflect positive x's across the y-axis. All right. What do you think's the next one we're going to do? Yeah, let's deal with that minus 1. What is that minus 1 telling us to do? Right 1. Great. What should we deal with next? The 2. Multiplying is closer than adding or subtracting. So when you're working inside out, multiplying is closer than adding or subtracting. Okay? So what's that 2 going to do for us? What do we call it? A what? Good. A vertical stretch. Okay? And lastly, we need to deal with this minus 3/4. So what's going to happen there? Good. Down 3/4. Great. Questions on that one? Aren't you glad we didn't make you graph that? Okay, let's practice graphing 1 because some of your homework is graphing. Okay? And remember, I said this works for any function no matter what. So it doesn't matter that we have no idea where this graph comes from. It doesn't matter that this doesn't look familiar. The rules still apply. Okay? So look at our our rules up here. We're going to work inside out. What's the first thing we're going to do? What's step 1? That plus 1. What's that plus 1 telling us to do? Left 1. Good. All right, so let's go ahead and do that. Take each point, move it left 1. And you might want to kind of like just lightly or dottedly draw in your graph so you know what it looks like. Okay? What's our next transformation? We're going to deal with this negative, right? What does that negative tell us to do? Good. Reflect across the x-axis. Okay, so do that with each of your points. On your homeworks, on your quizzes, on your tests, all that's really important to me is that I know without a doubt which graph you want me to grade. So whether that means you erase your first couple moves, your transformations, whether that means you dot it and then make this one solid, okay? Whether you darken it really dark or you use a highlighter, I don't really care. I just need to know really clearly which one is your final picture. Okay? What questions do you have over this stuff? Feel okay? Did you have to throw in the towel to math at all? No, you feel okay?
Nope. CKO.
Okay.